We'll just wait for a few minutes and then start. Okay. In the meantime, if you guys have any questions, I can take them also. Yeah. We'll wait a few minutes more and then start. In the meantime, you guys, if you guys have any questions, we can take that also. I guess we can start. Okay. I hope you guys can see my screen. We'll just recap a few things from last week. So last week we saw how typecasting in C, C++ works. So some of the things that we saw are like in general the concept of typecasting that we have in C or even C++. So implicit typecasting. So like where so let's say we define it I as an integer, f as a float, and d as a double, and then just try to print this. That's okay. But when we try to set I as double, right? D is double, so I is an integer. So when you try to set double as an integer, so here there will be implicit typecasting from double to integer. Okay. Here would have been the implicit typecasting from integer to double, here from double to integer, here from explicit. In this case, it will be explicit because we're actually specifically saying that we're typecasting with a double this bracket, and inside we're writing double. So the type to which we are typecasting to, we're explicitly mentioning it. So this type of conversion, typecasting conversion, is called explicit conversion. Okay. And then you can print the values after typecasting to see how the value looks, right? Similarly, you can even typecast from double to integer, right? So this is again a explicit form of typecasting. Now, thing is with the way of doing this brackets is the C style. Today we'll learn about the C++ way of doing the same thing. But let's go through the recaps, and then I'll start with the C++ style. Okay. Right. And then you can set the precision also, like um, that's part of this standard cout. You can just, while trying to output any number, right? You can even set the decimal places you want to print. So that is given by the standard precision. You can take a look at the function. Just try for yourself, right? Then in another example, we saw, so this was inbuilt, what do you call it? The inbuilt functions, the inbuilt data types. Now, from that, you can have like conversions, right? So converting from one inbuilt to another is pretty much straightforward, and it's okay. You can just do that. But while doing it the same for uh, pointers and like you have void pointers and others. So those you have to be a bit more careful. Okay. So here we can see that I have a double D. Okay. I have a pointer Q, which is of type double, like it points to it's a pointer of double type double. Okay. So if you try to do just Q equals to P, right? So Q is the pointer of double, and then P is a pointer of integer here. You'll get error, and similarly the vice versa. So pointer typecasting essentially cannot be implicit. Here we did not say anything and expect it to typecast to the other type. That's not allowed. Okay. But if you explicitly mention something like this, right? You're explicitly mentioning the uh, pointer you're typecasting to, like here. So that gets typecasted. Again, it has to be explicit for pointers. Here we see the double pointer, and similarly the integer pointer also. Okay. Now another thing is for pointers in general, you cannot typecast implicitly. Slight exception to that is the void pointer. Okay. So R here is a void pointer. Essentially, the value it points to, or it stores an address, right? And the value at that address essentially means the data type we do not know. Okay. So that's one way of looking at it. So what happens here is implicitly, if P is my integer pointer, right? So the compiler just ignores that data type, in the sense there is an address it stores. Okay, here I has some address with value 4. That address is stored in P. Okay, but when we try to when we write it this way, r equals to P, the same address is stored in R, but the data type itself is lost. That R doesn't know anymore that the storage at I mean the address at whatever the address is, that has 4, like integer. Okay, now uh, moving on, then if you try to cast a void pointer to any built data type, then again that will throw error. Simply because void doesn't know what data type it is. Implicitly, it is not allowed to do. You can explicitly cast it and then think of that address to be of integer type here, because that's not actually is, right? You can actually technically in system, it won't throw errors though, but during runtimes you might have garbage values if you try to do some other data types. So like let's say doubles or something. So essentially, essentially casting it to values higher than like bit storage, right? So casting to data types higher than the storage that you have will give you trouble. Okay. So while doing so, typecasting needs to be done carefully, and especially when dealing with this raw kind of pointers. Okay. Then we saw about A is like C style array. So this you can do. You're just pointing the same A. A itself is definitely a C style array, but A also stores the pointer to the block of memory of 10 integers. Okay. So doing a P equals to A is allowed and that works. But doing the same thing A equals to P doesn't work. I hope that is clear why, because P itself will just store a address, right? But A has to be a block of memory. So while yes, that block of memory is address is stored in A, you can't just overwrite and then just forget that address. Okay. I hope that is clear. Then some more examples. So typecasting with classes. Okay. So we define a class A, a class B, right? And then define corresponding objects of custom data type A, right? Small a is the object, small b is another object of custom data type B, or you can say it's the object of class A and a class of class B, right? Each of them respectively. Then we define pointers corresponding to these objects, right? So P and Q. So with defined as A pointer, B pointer, and then we just give the address. Now we saw that setting a object equal to another object gives you an error. So objects like so in classes you can't just set one object of another class to another object, right? That's something which is will throw error. Another thing is if you try to do the same C style array of typecasting, that is also not allowed. Here one would have thought that maybe implicit is not allowed, so I'll try explicit typecasting. Even that is not allowed. Okay. Similarly, if you try to do the reverse way also, it's not allowed. Anyway, it's essentially both A and B are of different data types in sense because that's how we defined it. So those are compiler will consider them as two different custom data types, and then they're incompatible. You can't convert from one to another. Okay. Similarly, the pointers also you can't just convert, but you can actually typecast the uh, address, right? So, something so get the address and then typecast the pointer to P and Q. This will give you some weird answers, but again, the compiler will uh, not complain here, but it's not actually recommended. Okay, right. Then we saw another example with void pointers, right? So where if you try to cast pointers to void, that those things will not throw errors, right? And yeah, especially so like I said before, if you have classes where they have no relation at all, like A is a different class and B is a different class. So converting one to another is not possible. It'll just throw you errors. But if you try to convert pointers or objects, right, from derived classes, right? So A is a public is the base class and B is the derived class. So when you try to do the um, conversion from derived to parent class, so those kind of things are allowed. So here you can see that A is small a is the object of class A, small b is the object of class B. Then we define the corresponding pointers P and Q. Define a void pointer R. Okay. Then we can like write P equals to Q. So we're setting the Q, which is of class B, right? That is the derived class, that as parent class, not an error. It won't throw an error. You can't set the base class to the derived class, but the derived class to the parent class. Okay. Or the base class. Uh, Moving on, then you can also set any kind of pointer, it doesn't matter what data type it is, to the void pointer, because implicitly it will just cast again. Here also there is an implicit conversion because there is information about derived class and there is essentially a relation between the derived class and the parent class, right? So here the compiler won't complain and you'll have implicit conversion. In this case, there will be also implicit conversion, and since it is a void pointer, there is not an issue in a way, if you can think about it. So compiler won't complain, and then especially since the data type is lost, that is absolutely okay to write a code like this. Uh, Naturally, the reverse is not possible because voids you can't convert implicitly to another data type, even if it's custom built or uh, inbuilt, right? Okay. Then we saw static binding, where um, depending on what kind of, so here we take example of a base class and with function f, a derived class with function f and g, and depending on what kind of input you have, right? Also here itself, again, naturally we define some objects. After that, we try to call the function. So now the function f here, which is called here, will be from here. Okay, because we don't give any data type. And what we do is we can also define f, right, in the derived class. Now, if we define it, it will override the original function that we have seen before. Okay. And let's say we explicitly say using some AF or something, right? Mm, yeah. So you can even get overloads, and G is just a naturally it's part of T, so that you don't have to worry. So essentially, depending on situations and some how you write some of the parts, the function that is getting called, okay, of any object. So when we call a function of some object, the type or the data, like which function it is calling, that is known at um, compilation itself, right? So that is the static binding. And if it's known at the runtime, like something like here, where we have virtual functions, so the base class here has virtual function, and even the derived class also we made virtual function. So it will depending on, so here we again made pointers, right? So depending on which object it is referring to, and we are calling the function, it will call the corresponding function. Okay. So here I put p as pointing to the p object. So when I call the function f, it will point to the function f of b. And when then we set the pointer to point to d, which is the derived class as object. The function refers to the f from derived class. Okay. So that's the summary of what we saw last week. Okay. Now let's see something uh, today. We'll look at, let me just see. I think it's called const. Okay, we'll start with const. Okay, yeah, right. Const cast. So we'll see the C. We saw the C style way of casting. Today we will see the C++ style way of casting. Okay. Now there are various. Sorry, there are various uh, methods in a way you can think of that C++ offers to cast data types and such, but each of them have their own role and each of them have their own properties. Okay, now let's understand one by one. So the first one we look at is const cast uh, function. Okay, now so far I guess the casting, the type casting is clear, right? I hope if anybody has any questions, do let me know. But that's essentially the summary. Okay. So let's look at the const cast operator. Okay. I'll draw an example first. Okay. So essentially what const cast does is it allows you to first we'll have the IO stream to print, of course, and then we'll have a return sorry, then 0. Okay. Now, essentially the idea is that with when you deal with pointers and references, those can be of const type. Okay. But the data they are referring to by reference or by pointer, that need not be const, like, okay, qualified. So to modify those kind of data types, we use this. So let's just see with an example. Okay, I'll give a simple example. Integer I equals to 0. Okay, we'll define an integer I, and then we'll define a const, maybe a reference first. Okay, so const reference ref. Okay, we'll put it as I, and then const integer pointer point equals to address. So the first one is essentially the I itself, the reference to I. Ref is itself I itself. Okay, and point stores the address of I. Okay, whatever I is in the memory. So point can point to the value. Okay, and both of them should just give 0. Okay, I'll maybe put it here. Yeah, shortcut. Right. Now, what we can do is, let's say you want to modify the value I, but through ref and PTR. So just doing ref equals to, let's say 9. What do you guys think will happen? Let's try to compile and see also. Yeah, good. So again, the compile itself through the error, so that's good. It's something also what we should expect, because what we're trying to do here is there is a reference to something. Okay, we are trying to modify, but the reference itself is also const data type, okay, const qualified. So we can't directly change that reference. But let's say we don't do this. Okay, this will obviously throw error. I hope this is clear. This so far it is clear. Okay, so what we'll do is we'll do const cast. Okay, and then give the data type. So it will be integer reference. Okay, and pass the reference itself. Okay, and then we use this to set to 9. Okay, so it's essentially the same idea. Obviously we can't use the syntax, but the idea is same. We want to change the value point, like whatever reference is referencing to 9, but because reference itself is const qualified, we can't change it directly. So we have to use this syntax in a way, you can think. So that's the const cast syntax, where it takes the data type. So here will be the integer reference, okay, and then just set it to 9. Let's say this qualifies. Okay. Oh, my bad. I did not print it. So maybe I'll do like I itself. Before changing this and then after changing. Okay. So great. As we can see, the first value it prints, the first line it prints 0 naturally, because that's what we have set to. And then after casting the reference, setting it to 9, it prints 9. Okay. I hope this is clear. The essential idea is that uh, when you are when you have a reference and it is const qualified, but the value it is actually pointing to I, okay, that is not const qualified, because do note here there is no const, it's just integer. Then this const casting will work. If you have const before this even this won't work, and ideally you should not even be changing the actual value, because you have said that it is constant, and compiler should it has to keep maintain the rule that since you have said the I is constant, I won't change it afterwards. Okay, great. So similarly, we can take example of doing the same thing, but with the pointer it is pointing to. So we'll just do a pointer and then ptr. Okay. This time I'll set it to 11. Okay. And then let's just print the same value. Do note I am just printing I itself, because I hope that is clear why I'm printing I. Okay. And here also, here also, here also, like all the three places. The reference ref is referring to the variable I itself. Okay. So essentially there is no distinction between I and ref. You can think of them as the same thing. In case of a pointer, the address of I in memory is stored in pointer. So whatever value I holds, pointer can change it. No, pointer will point to that, and through this method we can change it. Okay, great. Let's print that too. Okay. What happened? Did I make a mistake? Okay, okay. I did cast it, but I forgot to dereference it. Okay. I hope this is clear. So essentially think of this whole thing as this reference, and I'll write the error one also, so that this line is clear. So ptr equals to 11. This is what we want to do. So we dereference the pointer, right? Like this way, and set the value. The same thing is essentially done through this line syntax. Okay, right. So this is the C++ way of doing this, right? Then, okay. So what if I'll just give another example. Okay. Now, so far what you have seen is I as qualified as integer. Now, what do you guys think will happen when I try to compile this code? Anyone? Okay, maybe we'll see the output itself. It should throw an error, and surprisingly, it doesn't. Hmm. IS0 const reference. Hmm. Ideally, it should throw an error also, but I guess it is Clang is written that way. Again, I've told this before also. Sometimes you'll see some behaviors across compilers being different. Ideally, you should not be allowed to do this. Okay, when you have const qualified variables. So as we can see, it did not even throw an error. It just did not change anything and just printed the output. Okay. Anyway, ideally this should not be allowed. Okay. Right. Let's take another example. Call it um, you have as it should be IO string to print. And that takes care of that. Now we'll see the same thing in class in the context of a class. Okay. So let's define a class A. Okay. Then I'll have its private variable I underscore. Okay. And write its constructor too. So I'll define it in public as A. It takes an integer I. Okay. And then set I underscore to I. Okay. And then this will be the end of the constructor. I don't need to do anything else. So I'll just end with empty brackets. After that, I'll define another function, okay, integer get. It doesn't take any values, but now thing is it is also const qualified. Okay. Now with that, I will have a body of it, which will be just return I underscore. Okay. Now the idea is that get will just return the uh, private variable, okay, through a function. Like so, this is public. You can call this function and get the um, private variable. Okay, this is one way of accessing private members. Also, what we saw previously. Okay, then I'll set a void function which doesn't need any data type to return, so hence void. So it will set to integer whatever it takes it as input is some integer j. Okay, then I underscore equals to j. So it sets the private variable in I underscore right to j. Okay, so that is that, and then we end the class. That's it. To make things easy, I'll define a print function. So it takes um, character enter str, then body is standard cout to str. In the main, we can just format this to the key. The main function will make a const character. Okay, we'll call it yeah, sure. See, why not? With hello world. ended. And then mm, yeah, what we'll try to do is we have defined what do you call it? Um, yeah, sorry. So we have defined a class here. Okay, right. So we have what we've defined is a class A. Okay, and then a function print, and then use this to uh, play around. Okay, now the class itself has a get function which is of const and a set function, and we have a print function. So we set the const C with character type like const character. Okay, it, very important. This is const now. Okay, then let's say we try to print C itself. Okay, now thing is you will have sorry, my bad. Yeah. Now thing is you'll have C is character C is of type character pointer, right? Sorry, C is of type character pointer. Now that input is fine, you can give that, but remember it's also of const. Okay, let's see how the output looks for this. So it's a subtle thing, but one has to be careful because data types like this will not be taken. So it will throw exactly. So it will throw this error matching function for call to print. What we're trying to pass is const character pointer, and string has and but parent has only character pointer string. Okay, so normally you can't, if something is const qualified, it has to even the parameters or the arguments to that function also need to be of the same type. Okay, then you can even pass them. So this would have thrown an error is what we expected. Okay, so one this is how do I put it? This is definitely problematic if you try to just directly print it. But like we saw just before, what we can do is we can use const cast, okay, and then print the same thing, and that should take care of printing this, and we don't need to worry about we, some like we don't need to even worry that sorry hello, I'm audible, right? Okay, yeah. So right, so the thing is with using this const cast like just give me a minute. Yeah, sorry. Yeah, so like I was saying, so the nice thing about this const cast is with this we can temporarily, in a way, you can think of it like you're ignoring the constness of a pointer or a reference, okay, and then using then you can then pass or print or change the data or something. But again, the original thing also should be not const qualified, because here we just point to some C of character, like it's of character data type, right? Character pointer. So C's value can actually be changed. It's just that the pointer itself is const qualified, so we can't directly change it. Okay. So what we'll do is again const cast and then give the character pointer to it as a template. Okay. And then pass C. Okay. So essentially what this whole thing does is this print C, but with the constness of the pointer removed or ignored. Okay. Now let's see how what happens. Okay, great. So it prints hello world. The percentage is essentially the end line for terminal CSH terminal. So ignore that percentage. But the I hope the idea is clear. So here we use the print function to take the character C, okay, and but because it can't take it, it cannot take it directly. We typecast it using a const cast, okay, to ignore the constness and then print the string. Okay. That is one way. So, but let's say I have same thing, but this way. Can anybody guess what will happen to this program? The thing I changed is I commented this line. I'm trying to print C, and I have uh, changed the argument qualifier also. Anyone? Okay, let's compile and see. Ideally, it should not throw an error. Yeah. So thing is, because the constness of the character C is still there here, like it's still present. So str is still okay, sure. So what I'm saying is, I at first I wrote this function. Okay. Uh, Ignore this one that I just wrote. But so initially I had this function print, okay, which to character pointer str, like string str is the object as the variable of data type character pointer. Now I have defined something of character pointer C, or you can think of it like just another variable, or I'll just call it str here. It is fine. You can think of it like the same variable, but it's actually not the same. But for distinguishing, I'm just calling it as C. Okay. You can think of it as str itself. But the idea is that here C, which is hello world, okay, is const qualified. And when you try to pass to print, okay, here print doesn't have the const qualified data type. So it doesn't know how to, you cannot pass this to print. Okay, so it has to be a character pointer string and not const qualified for this print function. Okay, so for that, what we do is we comment, I'll just comment that. So what we do is we use a typecasting, which is called a const cast, which it might seem like it is casting to a const, but actually it doesn't. It's the opposite. It does the opposite. What it does is it casts away the const. In a way, you can think of it like it removes the constness of the pointer. Very important. It removes the constness, okay, of the pointer or the reference, like we saw here. Okay. The idea is that you cannot change a variable if it is const qualified. That is not going to change. Only thing here, what we're doing with the typecasting is the pointer or the reference to that variable is being changed. Okay, so using because this reference and the pointer, okay, they are const qualified, but the variable itself they are referring to or pointing to are not const qualified. Is not const qualified. Hence, you can change that value. Only thing is, because we are just currently because of various reasons, you can have a reference or a pointer which is of const type, but the value itself need not be of const type. So to change that value I, okay, through reference or pointers, you use the const cast typecasting. Okay. Now, I hope this part is clear, Simran. So what I'm doing is I am casting the const cast. I'm using the const cast, okay, with character pointer as the template to cast away or the constness of C and passing it to print. Now print will easily print this string with no problem, because for this line the C is treated as a character pointer, not a const character pointer, a character pointer. Okay. The other side of this is you can actually choose to have this function same and pass C, but as we saw, if const as we saw, character pointer won't suffice. So what you can do is you can actually overload this function. Okay, so due to overload, now actually I can have both of them. That's okay. Just that this won't throw any this time. Now what we're doing is same function now has two kinds of arguments. It takes character pointer and it also takes const character pointer. Be very careful. These are actually two different data types. Just you might think that because I'm calling const, it just means that the pointer can't change. Well, yes, but to the compiler, these are actually two different functions. Well, it's a overloaded function. It's the same function print sure, but compiler will treat it as two functions, like because it has two arguments. Because now I have a definition with const, right? When I try to pass C, which is const character type, the compiler will use this function to print it. And it doesn't need to worry if we have a const, if we have a character pointer also. Now let's see that. Yeah, it prints hello world. And previously it just having this threw an error, right? So let's see. Yeah, that throws an error. But now having this function, I can just comment. And if I have just this function, also it is okay. Because print C will use this function to print hello world. Okay. Is that clear, Simran? Okay, great. Moving on, we'll see another example. Okay, now with classes, right? Uh, Maybe I'll move this to another file for now and then yeah, use the same. To avoid some confusion. Yeah, that's okay. Yeah, that's it. That's three. Okay. Now we'll focus on the class that I created, right? So so I hope this part is clear. So let's have the original function and comment this. Right. Yeah. So here in this, for this print example, we need to cast like typecast it for it to work. But what happens when we try to define an object? So this is from perspective of argument sake. So like it takes argument, or you want to set some values. Okay, in that perspective it is okay. But what if the reference or pointer is custom data type like this? Okay, and then we call a dot get. What do you guys think will happen? A is a return type, so maybe I'll just print it off. I can't use this print function. Can anybody tell why? I want to print this a dot get, but I can't print this. We use the print function. It's simple actually because the get function is an integer. I can't pass integer to this. Print doesn't have any definition for that. Okay, so I have to explicitly use cout to print this. Okay. Yeah. Uh, okay, so I see what happened here. I'll just end the line to see it more clearly. Value of maybe just I'll call it I underscore yeah. Or in mm, oh, I'm sorry, I bet. This has to be here. Yeah. Okay. So that's I think this is okay. So what we've done is the original hello world. I just added an end line so that whatever I prints in the next line. So I have an object A of data type A, capital A. That's the class that we wrote, custom data type. And now it takes the value I 1. Now I wrote a constructor for it also. So where it takes the argument I, sets the I underscore, which is the internal variable, to I. Okay, that's it. That's what the constructor does. So now currently the I underscore is set to 1. And when I try to print it, okay, a dot get, I get that value and then it prints. Now, what if I do this? A dot, I also wrote a set function which takes a value and sets the internal variable. Okay, so let's say 7. What do you guys think will happen? Okay, any guesses? Okay, we'll just print it and see. Yeah, throws an error. The reason for that is set the object is of type const. Okay, that is hence it is not allowed. So the object that we created is of const. So it's like you can't set it to like how to put it, the its internal variables like just like that. Okay, what we can do is instead of doing this, okay, this throws an error. Okay, I'll make a note. Sorry. Hmm, right. Mm-hmm. Also error. Yeah, that's it. Right. Since this is an error, there is, as we have been seeing now, what we can do is we can use the const cast uh, function. Like, yeah, it's a function actually. Pass the data type a ampersand the reference to a, pass the object. Okay, then use the set function. So we have to set to 7. Yes, right. So essentially, what we're doing is instead of treating a as a const, we're treating it as a non-const. That's it, of just a. Reference is because it's essentially you can think of the whole thing like it will give another variable but of the same reference. Okay, so that we don't have to worry about essentially there'll be temporary variable here. You can just think that way. I'm not creating any pointers, and I want to ensure that this object is itself is gets modified. Okay, not some other temporary object that gets created and gets set. Okay. Yeah. Oh, right. Now I did not print it, but okay. So thing is, it not throw at least the compilation error. We should see the output also. Now I can't access the internal variable which is set here, right? I have to use the get function. So let's see. Initially, the value was set to 1, so that's what it printed, right? And then now it's set to 7, so hence it is printing that. Okay. I hope this is clear. This is the const cast uh, function. This is essentially the typecasting that C++ provides us. One noticeable thing to know that it is a C++ way and not a C way is because it is using templates, and those are not available in C. Okay, so rest assured, this is the C++ way of doing things. Okay. Yeah. Another thing we can see is, sorry, what if instead of this, we try to do this? Okay. What do you guys think will happen? Any guesses? Okay, I'll try to compile and show this. So it throws an error because essentially what we're trying to do is um, convert const a to a. That is not allowed. So you can't just remove the constness of an object. Okay. Here the internal variable I itself is not const qualified, hence we were able to change it. Okay. Set function is also okay because it's changing a non-const value, so it is fine. And here is just a return, so that is okay. And here the const qualifier is there to essentially say that this function doesn't change any internal variables. That's it. That's the idea behind this const. Here the object itself that was created is of const a data type. We can't just remove the constants of that object itself by doing this. So this is not allowed. This throws an error. Now, so to get around, we use the reference to the object, okay? And the reference itself, we are saying uh, with a we cast away the constants and then set the value, because the value I or I underscore here is not constant, so you can change that. Okay. I hope this is clear. Okay. So we saw how to remove the constants using like the C++ style. Let's see the same, sorry, same thing in a C style also. I'll go back to this example and do the same. So what you do is same thing, but you have to just typecast it. Const integer reference. Yeah, and then just okay. And similarly here, const pointer. It is a pointer, sorry. Oh, uh, yeah, sorry, not const. You are actually casting it to integer pointer and integer reference, and then changing it to 11. Okay, same idea. And here, what you can do is instead of this line again, you can have like print another character pointer casted. C is casted as character pointer, and then just passed. That's it. So this line won't work if you have just this line, right? Okay. I hope this message, this portion is also clear. Essentially, what I'm doing is I'll maybe comment this and show. I'm writing the same thing. which this won't work. So this is the C++ style. Casting. Uh, uh, okay, maybe this I just for like because we have been using that lingo, I just get const casting, and this is the way style. Okay, let's see. That should also be okay. Yeah, right. So as you can see here, essentially what you're doing is temporarily thinking of C, which is a const character pointer type, as character pointer, and then just passing it. Both of them do the same thing. It's just that with C++, you have to be more explicit. So what function are you using? You have to actually mention, give the type itself as a template parameter, and then just cast it on the object or the variable. Okay, right. Then what else? Yeah. So we saw const cast data type. So now we'll see the static cast data type. Okay. Okay. So let's take some examples to understand this. I'll have the name as usual. Return type would be zero. Return free integer type and just return zero. Then I'll just define some inbuilt data types with some variables. So like let's say integer I equals to 4. Then I'll have something of long. Okay. Long will be L, let's say, uh, equals to 10. Then double can have, right, which is F, or no, let's call it D, as 4.5. And then integer pointer. The pointer, I'll call it ptr I as I can just use the address of I again to point to that. Okay. Then a double pointer, which will be like ptr D, and set it to D, address of D. Right. Then I can have a void pointer as usual. Uh, okay, so ptr, that's it. So few inbuilt data types and then few pointers, right? Now let's write some code. I'll just write them like this. So I equals to D. Let me just write them. Then I equals to, okay, maybe I'll explain them. Okay. One another way is, so let's go line by line. Uh, we saw this before. So essentially, this is the implicit typecasting, right? So where you're trying to write an integer, okay, cast a double as an integer. Okay, this is implicit typecasting. Now, compiler will do it automatically, but if you want to make it explicit, we saw an example before, which is this. So essentially, I'm using the bracket to note to actually denote that I'm trying to convert D to an integer I. Okay, which is 4, sure, but right now, and D has 4.5. And again, probably this will convert to same 4 only. So maybe I'll just change it to 5 so that the output will be clear later. I can actually print this. So let's try to see the output. and then later on to, yeah, okay, right. So I think the output and the compilation, everything that is passes and output is also there. I think I hope the output is also clear. So far, we have just defined I for this part of the code at least. You have defined I, printed it, okay. Then set D implicitly, and maybe I'll just comment this and show you guys. So there's an implicit casting where first it prints for sure, but then when I write I equals to D, there will be an implicit casting, okay, where D, which has 5.5, will be stored as an integer. So it will be just 5. And again, printing it afterwards, we see the same thing. Same thing you can do. I'll comment this line first now. And this is the explicit. Okay, so this is the explicit type casting where we are explicitly saying that the D, which is a double, will be converted to an integer by using this typecasting method. Now this method is the C style, okay, C way explicit typecasting, okay, and let's see the output for this also. Yeah, 4 and 5 as expected. Now, um, since this is a C++ course, so we'll see the C++ way also the same thing. So I hope this is clear. This is the C style of typecasting. Now we will see the C++ way of typecasting. Sorry, we'll use static cast. Okay, then give the data type. So similarly, what we're giving here, the integer, and then pass to D. We have to actually give it inside a function. Yeah. And that's it. Yeah, we're good to go. Okay. It's the same thing. It's the same idea where you're doing an implicit cast or explicit cast. And here also it's an explicit cast, but the difference is that this is the C++ way of doing this. The reason to use this instead of the C style is that it is much more clearer exactly what you're trying to do, because sometimes it can be confusing what is happening in some of the because you'll have brackets and and sometimes this pointer also looks like a is also used for multiplication. So being as explicit as possible is actually the best practice. So in C++ at least, it's better to use explicitly. Are you going with a const cast? Are you going with a static cast? And you'll also see more kinds of casting. So being explicit is always better and it makes your code more readable. Okay. And also the benefit is that because it is templatized, right? So if sometimes when you have errors, right, it will also throw those and you can actually work with them. Uh, because in C style, it's not meant to be written with some errors and such. So you won't get those here. But at least when you go with any of the C++ way of doing things, is here I'm just giving an example with we're seeing with the typecasting, but in general I'm saying. So you'll have more errors if you make mistakes or if you run into segmentation fault. We are doing some out of bound access. So using vector actually makes more sense because anyway, you would have allocated the memory. It just makes the bookkeeping of all the stuff makes it much easier if you use standard vectors, because it inherently has the knowledge of the size it wants to store. You can dynamically reallocate it also, and yeah, there's this, and you can use other um, useful functions defined in standard uh, namespace on that standard vector also. So overall, all in all, like there are a lot of reasons to go with this C++ way of doing things while writing a C++ code. Yeah, hence. So that's the motivation there. Okay. So this will be also explicit typecasting. Let's print and see. I think that's correct. We get the correct output 4 and 5. Okay. Now let's move on and then see some other outputs. So let's say d equals to I. Okay. And then d equals to double. Sorry, I. D equals to static cast double, and then it takes I. All of them are the same. Essentially, the idea is the same. Okay. Instead of just doing a cast from a double to an integer, we also can cast a integer to a double. Okay. Same idea. So this will be implicit typecast. This will be C style, and then a C++ type. I'll just quickly run each of them again and show you guys. Here it will be D. Okay. So the first two outputs are 4 and 5. So those what did I do? Yeah. Since here the value was changed, so hence it showed 5. Let's ignore this part of the code for now, so that I have 4 itself in integer. Yeah. Okay, great. So if I try to print D, it will be 5.5, which is initially set. And then when I try to set D equals to I, where I is 4, it should print me 4. Yeah, that's it. Okay. Each of the typecasting should work exactly the same way. Should have 5.5 and 4, right? There is code wise, there is essentially no difference. Okay. But the syntax matters. Hence the all this exercise. Okay. So I hope this idea is clear. So we saw implicit typecasting before, and also saw explicit typecasting, which is a C-style typecasting. Today we are learning the C++ way of explicit typecasting using static cast. And also we saw const cast also, where you sort of ignore the constness of the pointer or the reference if it is const qualified. Okay. And yeah, let's take the example of pointers too. So we saw the first ones, so like double and integer. So let's take the pointers too. So I'll have pointer v that I wrote, okay, equals to pointer, let's say I say I, same thing with v. Now, and it will tell if it's okay, not okay, anything to do this. Will I get errors or compilation error, runtime error, anything? So yeah, to recall, the pointer I is of type integer pointer, pointer v is of type void pointer, and pointer d is of double pointer type. Okay. If I run this, maybe I'll just make another file for this. Already getting a little crowded in this body, so maybe I'll make another file. Yeah, these all are okay. I'll just remove this. Okay, that got deleted again. That's okay. I'll write it again. So v equals to I And then okay, I can have the full thing. This also are okay. This is fine. Okay, great. So yeah, I'll take another example with just pointers now. Okay. So nice. So what we'll do is now that was what we saw for explicit and implicit and C++ style of doing for just normal inbuilt data types. Okay, integer doubles and so on, vice versa. And let's look at the pointers themselves. So this is the example that I was trying to look at. So it will be okay. Can everybody guess what will happen? You will throw me error, compilation error, runtime error, or anything. Okay, won't throw any errors, and that's what we see also because remember this is a void pointer type. So implicit conversion from any data type to void pointer is allowed. Okay, obviously the reverse is not allowed. Right. Then what we can do is, let's say we write the reverse thing. Pointer I, okay, equals to pointer V, and same thing, D is pointer V. Okay, can anybody take a guess what will happen now? In this should throw an error because you can't change up the type void type to any other type implicitly. Okay, but with typecasting you can actually do a conversion. So these will throw errors. Sure, make a note. Okay. So to do the same thing, what we will do is do it both ways. So one is cast it to whatever pointer I is. Just look at here. It is of integer pointer. So just use the C style to cast it. Okay. Right. Then let's see. Yeah, successfully compiles. So this is you can use C style to cast even pointers from let's say void data type or something to the uh, other data type that you want. Okay. Similarly, you can even cast doubles, right? And here it has to be double because you can't cast it and write to a different data type. That's not allowed. Okay, this is also okay. Passes. Let's for completeness do the same with because these are C styles. C style. Let's do with the C++ style also. Static cast, yes. And here too. Did I miss? Oh yeah, my bad. These are functions. Do remember. So they need to take the object or the variable as the input. So yeah, like I was saying, I mean, you have to be explicit with these expressions and syntax. So hence it actually avoids making mistakes and errors. So like you just saw now. So when you're using C++, it's actually highly recommended. It's actually a good practice also to use all this C++ syntax and C++ way of doing things rather than just the C way because it makes your code more readable. It helps you in finding bugs and so on. Okay. Uh, right. Um, in that case, I guess we can move on to the other type of cast. So far, if you guys have any questions, do let me know. Feel free to ask. I think we can take a little pause here and then just look at all the examples we saw. So first is the cast type, okay, where the reference or the pointer itself, if it's of const type, we recast it such that we just ignore the constness and necessarily the uh, variable that we're trying where they're pointing to it has to be of non-constant. Then we can just ignore the constness and then change the value. Okay, that's what we saw here. Then we saw same idea, but here we're trying to pass to a function. Okay, here it's not just a function, it's also the uh, an object which was declared as a const, but the internal variable is not const type. Okay, hence we were trying to change it. Okay, by doing away with the constness or like temporarily in a way. Now, another example we see is of for static cast, where there is implicit casting or C style way of explicit casting. That's this, and explicit C++ style way of casting, static cast. Okay, you can convert from all these inbuilt data types like ID and vice versa and so on. That's what we see. Then after that, we see also you can do the same thing with the pointers, the inbuilt data types, but with the pointers of them. So this will be the C style. And then just make it here too. And this will be the C++ style. Okay. I hope so far so good. Before we move on to the next type of casting, does anybody have any questions so far? Okay. Moving on. So we'll go with reinterpret cast. Okay. Let's take an example to understand reinterpret cast. Okay. Right. So I'll define a class A. Okay. It's just simple, nothing special about it. So just dummy classes with empty constructor, and obviously we'll use the default constructor, but inside of the body there is no, it's empty. It doesn't have any internal private variables or functions or anything. Just a simple one. Then we'll have the main function, okay, with the return type 0, and then we'll define something called long L equals to, let's say, 8, and double D equals to, let's say, 5.9. Okay. Then I'll define a pointer. Pointer ptrd as pointing to the same, like, pointing to the same D. Then what I'll do is do it this way, equals to D, one line. Then another is with L equals to no, yeah. Maybe before doing the usual that we saw before, what do you guys think will happen right? So I have defined a double, a long, a double. a double pointer, and then just write L equals to D. Obviously, I hope this is clear that this line itself is um, implicit way of typecasting, right? Because we have two different data types and then we are not mentioned anything. So it will be implicit. But how do I put it? Will it throw an error? Do you guys think? Or will not throw an error or anything? Or runtime error, compilation error, anything? What do you guys think? Okay, you can run it and see. Yeah, ideally it should throw an error because implicit castings like this should not be. Oh wait, my bad. I meant to put the pointer. Yeah, so that casting is okay because I'm sure. Just want to check something because longs can be of different sizes, right? Uh, Size. I just want to check in my system what that is. So size of long, then I'll just end it. Comment this one now. Okay, yeah, eight. Hence, it was able to easily do it because long takes 8 bytes, double also takes 8 bytes in my system at least. So not an issue. Otherwise, you have to use long to get to the higher bits if supported by your OS. Okay. Yes, that's okay. So now, yeah, what I meant to do is actually this. So what do you guys think will happen? Okay, let's run and see. Yeah, throws an error because what we're trying to do is exactly the compiler error itself tells us uh, we're trying to uh, pointer to integer conversion to long from double pointer. We have a double pointer. We're trying to put into a long. Okay. Now, what we'll try to do here is use the reinterpret cast to change the typecasting. Okay. And let's see how that will work. So what we'll do is write the same thing. Now, instead of just having pointed you obviously, we cast it as long and then do the same thing. Okay. I'll mention a note error. Okay. So do you guys think it is enough? Like if I just cast it and then run this? Okay. Let's run and see. Yep. Oh, of course. My bad. It should throw error, so I'll just comment this one. Yeah. Let's run and see what happens. Yeah. That is okay because you can cast again using the C style. Okay. Again, I'll make a note. Uh, Another point, all these codes that I discuss in these sessions, they should be available to you. The Google Drive link to that should be shared with you guys. If you don't have access, please do contact the NPTEL support for accessing these, even the lectures also. They're available in YouTube. I just upload them to YouTube, and the links to each of them should be available to you guys. So if someone doesn't have access to the YouTube links or all of these codes that I discuss for every week, please do reach out to them. They should be able to help you guys out. I can actually just put them in the chat also. Just give me a minute. Yeah, chat. Yeah. So this is the Google Drive link. and the playlist link also I'll just share. So I've made the all the videos into a playlist, so you guys can take a look at that also. Um, yeah. So feel free to access this later. Okay. Yeah. Coming back to this. So this is the C style of explicit typecasting we did. Now let's do the C++ way. Now thing is here we want to use the reinterpret cast. Okay. So and we'll just pass the type and put that as a function. Okay. Yeah. Okay. Now let's run it. Okay, great. So both of them work and they did not throw errors also. Okay. So this is the reinterpret cast usage where you want to change typecasting. Okay. In this is the C++ style of it. This is used like why do we have even reinterpret cast if we have static? So reinterpret cast can change data type from anything to anything actually. So that's the idea. It converts any pointer type to any other pointer type, even if they are unrelated classes also. Okay, so that's the use of it because sometimes static cast may not be enough for the use case. So that's where the reinterpret cast comes to the rescue. Syntactically, for C, it doesn't matter in a way if you think about it. C will have the same syntax, but in C++, you're much more explicit with your syntax. So like you're actually specifically saying if it's a static cast or uh, reinterpret cast or any such thing. So again, like I have been repeating myself, but that's the nice thing about C++ is you're being more explicit. So your code is more readable and you're uh, conveying the exact message that you want your code to do. Okay. So hence the usage of all these syntaxes. Okay. Okay, great. So yeah, with this the today's class, I'll just have this much, but if you guys have any questions, I can take them or yeah, please yeah, you can feel free to leave. Yeah. I'll be here. If you have any questions, do shoot up in the chat or ask me. Okay, I guess we can end the class today. So, as usual, I always encourage to practice questions to understand these concepts, and you'll obviously find all these codes that I discuss in a G Drive. So, do go through them yourselves also, try them out, and yeah, if you have any questions, you can ask in these TA sessions. Also in the forum, also if you have any questions, you can post your questions there. And yeah, happy programming.